Okay, let's start. Welcome to everybody. Thanks to everyone to attend this webinar. I'm Claudia Cecchetto from University of Padua, and I'm here with Gianluca Ruffato from Department of Physics of University of Padua, and also Attilio Zilli from Politecnico di Milano, and two experts of photonics. I will introduce briefly today's seminar. So this initiative is called FNIP, and that's Fluorescence, Neuroimaging, and Photonics. It's an interdisciplinary program started by Anna Archetti in the University of Padua, and has three main topics. The first topic is the one that we will treat today, and it's photonics. And this topic investigates basically how to control and manipulate the light and its properties down to the nanometer scale. And within this initiative, we will explore how photonics is advancing the design and fabrication of optical components and systems. The second main topic is microscopy, in particular fluorescence microscopy. That is a technique that can reveal the structure and function of specific layers within and between cells with optical and light-compatible approach. During these seminars, we will investigate how the fluorescence technique combined with other tools can improve 3D imaging. The third main topic is the software and all the image processing methods that are available and developed to extract and analyze features of interest from the digital images and from basically imaging data. The community will explore how to perform neuroactivity analysis and how to benchmark function imaging methods. This initiative is a bottom-up initiative from centers and departments. It started from Anna Archetti, as I already said, from Marco Dal Maschio lab here in the biomedical science in the University of Padua, and also from the National Research Council with Dr. Mariotti and Dr. Brondi, and with the help also of the Department of Physics with Dr. Borile and Dr. Gianluca Ruffato that is present today. Other supporters of the initiative are around the Europe. We thank Professor Tagliabue in EPFL, present today as well, and also other players in UK and in Italy. The speakers that we will have during these webinars and during the FNIP Day are from all over the world. In particular, today we'll have three speakers from France, Switzerland, and Finland. You can join us for other events, other webinars by visiting the dedicated webpage, and you can also see when there will be the next webinars. You can also join us in person, so we can meet in person and have fruitful discussions together during the FNIP Day. The day is organized for the end of September, September 29th, and it will be in Padua in the beautiful setting of Palazzo della Salute here in the center of Padua. So you can join us for the webinars, for the events, but you can also join us as a speaker or a supporter and an organizer. Please communicate with us if you are interested in joining us in other in this way. So as I already said, today it's a session about photonics, the first main topic of FNIP. We will have 3 speakers. The first speaker will be Professor Martin from EPFL, and he will talk about the optical nanostructures and nanofabrication. Then we will have Professor Kaglian from Tampere University in Finland, and she will talk about rolled up multi-layer nanostructures and their applications. And finally, Professor Genevet from France, and he will talk about physics, application, and integration of metasurfaces. Just a few things about the webinar and the guidelines. The webinar will be recorded, and it will be later uploaded on the webpage of this initiative. You can use anytime the Q&A button to write your question and also to vote your favorite question. And during all the talks and during all the webinar. You can raise your hand to ask another question just in the follow-up session. And during the follow-up session, we will enable your microphone and you can be allowed to give your question to the speakers. If you have any question, please let us know. And I will leave the stage to Gianluca Ruffatto, that he will introduce the first speaker for today. Thank you.
So, thank you, Claudia. Good morning, everyone. I thank again our guests for their valuable presence. The common element of our talks is represented today by metasurfaces. Metasurfaces are a flourishing and transversal research field at the frontier of photonics, promising to replace traditional optics in order to advance the applications of light and enable new and still unexploited capabilities. With respect to standard optical elements, the structuring of matter at the nanoscale opens to a more sophisticated and versatile way to control and manipulate the degrees of freedom of light, such as intensity, phase, and polarization. Metasurfaces provide a paradigm shift in optics design, fabrication, and integration in a wide range of fields, from life science to information and communication technology. Metasurfaces are not just an evolution of optical elements, but a revolution in light manipulation and photonic devices, both at the classical and single photon regime. Today, thanks to our speakers, we will be introduced to this amazing research field and discover the state-of-the-art in metasurfaces fabrication and applications. Today's first speaker is Professor Olivier Martin. Professor Olivier Martin is a professor of nanophotonics and optical signal processing at the Swiss Federal Institute of Technology in Lausanne, EPFL, where he is head of a nanophotonics and metrology laboratory and director of a microengineering section. He conducts a comprehensive research that combines modeling with nanofabrication and experiments on plasmonic systems, with applications in nonlinear optics, biosensing, security features, and optical manipulations at the nanoscale. In 2005, he introduced the concept of an optical antenna, which is now widespread in plasmonics. In 2016, he received an ERC advanced grant on the utilization of plasmonic features and plasmonic forces to fabricate nanosystems. Between 2016 and 2020, he served as director of the EPFL microengineering section. He's associated editor to Advanced Photonics and Frontiers in Physics. So thank you, Professor Martin, to be here today and present this presentation. The title is Plasmonic, Allayed, and Hybrid Metasurfaces.
Thank you very much. Thank you for this very friendly but also very challenging introduction. I hope metasurfaces will hold all the promises you've made. I'm of course very delighted to learn more about this initiative, and it's also nice to see that we are so close together. So I guess this can also lead to very stimulating collaborations. So my field of research is plasmonics. And I thought that maybe some of you might not be very familiar with what plasmonics is. So let me give you a very simple introduction. Don't worry, this is going to be the only formula in the entire talk, but I need this formula to describe the light scattering by a small particle. Say we have a small particle of silver, for example, and this is illuminated with some incident light, and we want to compute the scattered light by this particle. What's very important to understand is that this particle is described by its permittivity, and it's a bit like the refractive index, and this permittivity strongly depends on the wavelengths. I mean, that's true for any material. Obviously, you have a nice window, I hope you have a nice window where you can look out instead of looking at the slides, and this window is made out of glass, which is perfectly transparent for visible light. But if you were to look at this window in the infrared, it would be completely opaque. So the permittivity, the optical properties depend on the wavelengths very much. And for the scattered light, it's described by this formula that has two terms. The first term here depends on the radius of the particle. The larger the particle, the more light it will scatter. But it's also inversely proportional to the wavelengths, which means that it will also scatter a lot of light for very small wavelengths. And this actually is the origin of the blue sky that I hope we can enjoy today. At least here in Lausanne, it's quite sunny. If you don't look at the sun, but look at the sky, you see the scattered light. And the shortest wavelengths our eye can perceive corresponds to blue, and this is why the sky is blue. In Plasmonic, we actually work with the second term in this equation, which only depends on the material. And you see here in the denominator, the permittivity plus 2. So if I want to make a lot of scattered light, what I can do is to try to make this term go to 0. And making this go to 0 would mean having a material where the permittivity, epsilon, is negative, and ideally it should be equal to -2. If I have -2 here, plus 2, it gives me 0, and again, dividing by 0 makes things very large. It turns out that in metals, the permittivity, and you have here experimental data for silver, the permittivity is negative. In red, you have the real part of the permittivity. And you see that this condition of having the permittivity equal to -2 occurs at a very specific wavelengths in the order of 350 nanometer here. So it means that at this wavelengths, there will be pretty much 0 in the denominator, and a lot of light is going to be scattered by this particle. And this is what we call the excitation of the Plasmon resonance in this small particle, a very strong peak of scattered light at a specific wavelengths, which will make the particle have a specific color. The peak is not infinitely narrow because, unfortunately, metals have a complex permittivity, so there is also an imaginary part to that permittivity, and this imaginary part, it accounts for losses, absorption. It's also probably useful for some of the things you'd like to do in your network, but it leads to having a resonance which is not extremely narrow, but has a certain width. But still, so far, with this very simple theory, we've learned that small silver nanoparticles should basically scatter light in the blue region. And if you have such a nice theory, it's of course tempting to make the experiment. So you can take colloidal particles, silver, they're all the same size, look at them in the dark field microscope, and what you will see is, yes, nice little blue spot here, but you will also see that some of these particles, they are green, some appear yellow, some even appear red. And this is very surprising. Actually, about 15 years ago, when I started working on that topic, we didn't quite understand what was going on. I was then at UCSD, and there was an amazing technician, Jack Mock, who took the same sample and looked at it with electron microscopy. what he observed is that this particle, which is blue, is actually a nice round particle. So it fits well with our theory. But this one, which is green here, turns out to be actually like a pentagon. And this one, which is here red, is just like a triangle. Probably some of you will say, well, it's not so surprising. This is just a geometrical resonance effect. And you are right. But what's very special is that this geometrical resonance effect occurs for particles that are much, much smaller than the wavelengths. Normally, when you have a resonance effect, you need to have something which is in the order of the size of the wavelengths. If you want to make a big resonance in your bath, you're not just going to wave a little bit your hands around. You're going to move forward and backward in the bathtub such that you make a big wave. So you're going to make a wave that has a wavelength which is comparable to the length of your bathtub. And here, with these plasmonic particles, we have resonances for structures that are much, much smaller than the wavelengths. Something to keep in mind also is that between the normal appearance of silver in that case and the nanostructure appearance, we have something very, very different. And also for the nanostructure, the shape really matters a lot. So this is very briefly a small overview of plasmonics. We speak of plasma because in these metals, we have a very high density of free electrons. So it behaves like a plasma, but it's not a gas plasma like you have in a fluorescent tube, but it's just a solid state plasma. And unfortunately, only very few metals exist where we can have this effect. These metals actually have a nice name. They're called coinage metals. So these are the metals that are used to make coins, like gold, silver, copper. And of course, each metal will have a different dielectric function. So it will have a different resonance at different resonance wavelengths. This condition, epsilon equal to -2, will be as we've seen in the blue for silver, but for gold, it will be in the red or even in the infrared, for copper towards the yellow, or for aluminium in the short UV range of the spectrum. So each metal is different, and we have only a few metals available for playing around with plasmonics. Now, I'd like to start by describing two main nanotechnologies that are used to produce these nanostructures. We have seen that the material is important, but also the shape of the structure is important. So we need to be able to fabricate nanostructures, dimensions sub 100 nanometer, but well-controlled shapes. And the very traditional approach for that relies on a positive photoresist and liftoff. So what does that mean? You start by having your substrate. Often it's glass because you want to look at optical effects. So you want a transparent substrate. On that substrate, you put your photoresist. Then you do electron beam exposure. We use what we call a positive photoresist. This means that where the electrons have exposed the photoresist, once you develop, the resist will disappear. And then they will remain hollows. And in those hollows, you're going to evaporate your metal, say gold in that case. The metal is evaporated everywhere, but it also goes here in the hollows. And at the end, you do this liftoff, which just consists in putting your sample into acetone. It will dissolve the remaining photoresist. The metal on top will go away, and you will be left with just the structure you wanted to fabricate. Maybe you've noticed that in that case, we use 2 layers of photoresist, and this is quite important. We put here this bottom layer, which is a bit more sensitive to the electrons from the E-beam, such that when it's developed, here the cavity is a bit larger. And as a consequence, when you evaporate the metal, there will be a discontinuous film between what is deposited on the substrate and the remaining, such that the liftoff occurs very well. If you don't do that, if you put only 1 layer of photoresist, when you do the liftoff, this continuous film will usually tear apart, and you don't have you have structures that are not very well defined. So that's the first approach. The second approach, which is less used, but I would like to advocate that it's probably superior in terms of the structure you can fabricate, relies on using a negative photoresist, a negative resist for the E-beam. So a negative resist, which is shown here in green, and typical resist would be HSQ. When you expose it to the electrons with the electron beam lithography system, this resist will become very hard and will remain here. And all around it will disappear. So it's the opposite. Here we would build a cavity with a positive photoresist. With a negative photoresist, the resist remains where it's being exposed. Then you put that in a milling machine. So you basically bombard with ions. You could also use reactive ion etching, but we don't have any reactive ions for gold. So here we just use argon etching, argon milling, and the ions will remove the material around the structures and the structure will be defined that way. So if we compare the two techniques, here you have different type of nanostructures we have fabricated in gold, but let's maybe focus on this one, the dipole antenna. So two gold nanostructures with a very tiny gap. You see that with the etching approach, we can really make a very well-defined gap, which is about 10 nanometers between these two structures in gold. If we use liftoff, the structures are not so well defined. We see also that they become a bit round. The reason being actually that because we have here this wider opening, the gold atom, they will diffuse on the surface, and altogether it will make your structure less well defined. With etching, you can get very, very accurate dolmen structures. So these structures have strange optical resonance that we call Fano resonance. It's not just a Lorentzian shape. You can make things like spirals. So you see this is possible with etching, but if you try to do it with liftoff, it's very hard to lift off the part in between. All the details about these different techniques are given with great precision in that publication, if you're interested. So we can fabricate nanostructures. These were examples made out of gold. That's probably the metal of choice for plasmonics. It's a bit annoying if you want to do optics because it works very well in the infrared, not so much in the visible range. Silver is another material, but we see that we don't have so many other choices if we would like to tune our Plasmon resonance. So a question we ask ourselves is actually, could we expand the range of materials with which we can do plasmonics? And something very trivial to do, since you know that gold and silver work well, is just to do alloys. So to mix them in different proportion, and then hope that by doing that, you will have nanostructures which will have resonances at different wavelengths. This works actually well if we just focus here on the dielectric function again as a function of the wavelengths of these alloys. You see that for silver, this is what we have seen previously. For gold, we are on the longer wavelengths range. But if we do alloy in between, so 50-50, 20-80, changing just the stoichiometry of the material, we can have different dielectric functions in between that of silver or that of gold. So that seems an interesting approach, but the problem is if you make an alloy, you have to do it at high temperature. And if you do it at high temperature, well, the question is, can we keep the shape of our nanostructures? Because we've seen that the nanostructures, the shape is very important for the type of resonance we have. So if we take some small bars of alloy and then we heat them to alloy them, unfortunately, they are completely green. And the thermodynamics is such that the shape that is going to minimize the free energy of this alloy is just a small sphere. So you end up having small blurbs on your surface. So the shape is completely lost during the alloying process. So the challenge we set us recently was to try to find a low temperature alloying procedure where we could keep the shape of our nanostructure and also change the composition very easily. Of course, you could deposit directly an alloy, but that would require a machine in which you have many different targets with many different alloys, and that's very expensive. So the recipe we came up with, and that was really just trial and error, is to heat only at 300 Celsius, so low temperature, but for a very long time, 8 hours, such that both materials will diffuse together. And we've noticed that if we really want to have a good alloy, we need to have a little boost at the end at 450 degrees for half an hour. The technique is very simple and allows any stoichiometry because, say, you want to make an alloy with 80% gold, you start by depositing 80 nanometer of gold, and then you put 20 nanometer on silver. You do this procedure and you have your alloy. If you want to have the reverse, just 20% gold, you put 20 nanometer gold, and then you put silver, you alloy it, and you have another alloy. And the good thing about this approach is because it's low temperature, the structures are perfectly well maintained. You see here a small triangle, it remains a triangle after the alloying. You see here a rod, it also remains a rod, or here, this is a structure that also has some Fano resonances, it remains nicely shaped after the end of the alloying process. And it is really an alloy. Between before and after the annealing, we see that the surface is modified. If we make some materials analysis like EDS or XPS, we see that going through the thickness of the film, we have homogeneous distribution of gold and silver. So in that case, that would be a 20% gold, 80% silver. And this is indeed homogeneous through the entire sample, whereas at the beginning, we had gold at the bottom and silver at the top. Now it's being perfectly alloyed throughout. Okay, so now we can do that. We were very pleased to see it was possible. The question is, well, what can we do with that? And if you allow me at this stage, I would like to stop sharing my screen and make an experiment. Experiments are always very important. We make a very simple experiment. We're back to the physics 101. We have a spring and we have a mass, okay? And I'm going to just move my arm at low frequency. And as you probably all observe, when my hand goes down, the mass goes down. When my hand goes up, the mass goes up. Now I'm going to do the same, but at high frequency. And you don't see it very well, but I can tell you I feel it. At high frequency, when my hand goes down, the mass goes up. And when my hand goes up, the mass goes down. So something has happened when I have changed the frequency. Let me go back to my presentation. Something has happened, and what has happened happens also in optics. We've seen that this small silver particle, when I get the Plasmon resonance, there is a lot of scattered light, so there is a lot of amplitude, but there is also a phase effect. So if, like for the spring at low frequency, when the hand goes down, the spring goes down, the mass goes down. When the hand goes up, the mass goes up. If we work on the other side of the resonance at high frequency, when the hand goes down, the mass goes up. And the same is true for light. So there is this phase change as you go through the resonance. For light, it works as follows. If you go below the resonance frequency of the particle, the incident light will drive the Plasmon resonance, and the scattered light is going to be in phase with the incident light. If you go at high frequency, above the resonance frequency, so say, for example, you take a blue laser, then the scattered light is out of phase with the incident light. So we have now, with these small plasmonic nanoparticles, something that allows us to modify the phase of scattered light. Now, is that useful? Well, actually, I would pretend it's very useful. And as you do a lot of microscopy, I hope you're easy to convince about that, because pretty much any optical component works with the phase. If you look at a grating will take the incident light and make it go in another direction. It means that if we look at the phase front, as the phase front arrives here on the surface, at this point, nothing happens. The phase is the same. But in order for the light to bend to the right, we see here, there must have been a little additional phase. And here a bit more, and here a bit more. And finally, we come to the point where it's the next phase front that is going to arrive at this point. So between this point and this point, we can understand the function of this grating as adding phase to the incoming light. The same holds for a lens. A lens, if you look at the ray in the middle of the lens, it just continues straight. But in order for the lens to focus, it means that here on the left, this part of the incoming light has been receiving some additional phase, say plus pi, so it goes on the right. And on the other end of the lens, it's like if you had a negative phase so that it bends on the left, and altogether it focuses. Now, of course, the most arbitrary or general type of optical component you can make is a hologram, where you have a very complicated phase distribution here. So the idea is, can we now use our alloyed nanostructures to mimic the effect here of the grating? So we will put different particles that will produce different phases on the surface. And for that, we just go back to our diagram. We have seen that we have between gold and silver different resonances. If we choose the wavelengths at which we're going to work, say here the black line, depending whether I have a gold particle or I have a silver particle, I will have a different phase. And I can make all the phase I wish in between just by changing the composition of the alloy. So of course, the challenge there is that you want to fabricate a sample in which you have different alloys with different stoichiometry that are all nicely organized on the surface. So you have to do successive e-beam lithography to do that. We've kept the challenge relatively modest because we've considered only two different alloys, two different stoichiometry, 8020 and 2080. And we have written the nanostructure one after the other. First, putting, say, 20 nanometer gold, 80 nanometer silver, then starting again, putting again photoresist, making sure we align, writing the voids for the next structures, evaporating the second metals, say now 80 nanometer gold, 20 nanometer silver, removing the resist and doing all together the final annealing. And like that, we have a surface on which we have different nanostructures. In the context of metasurfaces, we call that meta-atoms, so the constituting components of the metasurface that have different compositions. So when we're going to illuminate them with light at a given wavelength, they will produce different phases. And that's the result. This is this metasurface. If we zoom a little bit in, we see the different structures. You may say, well, they are not all perfectly aligned, but you must keep in mind that these are actually collections of different materials that have been done in successive e-beam lithography steps. So I think here we have a reproducibility or an accuracy in the placement of our structure, which is in the order of 20 nanometer between successive illumination. And with that, we can make a hologram, for example. We can make a Fresnel zone plane, so just a lens that will focus the light. And we see all this works in the visible range of the spectrum. For the Fresnel zone plate, what we have is just the nanostructures that are put in circles all together, such that it produces this phase change that we need. Let me move to the last part, where after having spoken quite a bit about metal and plasmonics, I would like to try to branch out to something a bit different, which is hybrid structures. One can understand that from a bit of a theoretical point of view, which is what we call the multipoles. The multipoles are basically the constituents of the electromagnetic modes in a structure, in a system. And if you're interested in that field, I'd like to point out the excellent paper by Carsten Hochstuhl, and he's written many others, but this one explains that very well in the context of metasurfaces. The plasmonic material that we've been using so far, they basically have electric resonances. Whereas dielectric materials, and we'll be using silicon in the next, they have more complicated resonances. They also have magnetic resonances and also higher order electric resonances. So it's a little bit now as if you would like to play Scrabble and make nice, interesting words. If you only play with metals, let's say you have only the vowels. But if you also include dielectric, then you can also have the consonant letters. And of course, if you mix the two together, the hope is to be able to have a more interesting vocabulary and make more interesting words. So to do that, we fabricated this type of nanostructures, which have a silicon cylinder at the bottom. That's the dielectric part. They have an aluminum disc on the top. And because all this is driven by the coupling between the two, we put a small glass spacer, SiO2 in between, such that we can control the distance between the two. You see here the structures as they have been fabricated. Here, silicon at the bottom, aluminum on the top, and in between the spacer made out of glass. The process is as follows. Actually, it's a combination of the two processes I've presented at the beginning. There is etching and there is liftoff. We start by depositing on our substrate the silicon in blue, the spacer in green. Then on top of that, we make a liftoff. So we have again our two photoresist, and using electron beam, we define a circular cavity in which we deposit aluminum. So here we have aluminum disc on top of this structure. And in the next step, we use this aluminum disc as a mask to etch away the silicon and the glass material. And here we could do reactive ion etching because that works for silicon and SiO2. And we define like this the structure. So if you want, the aluminum structure works both as the mask during the fabrication, but also as the plasmonic structure that we will need in the end for the resonance of our system. If we analyze a little bit the response of that system, here on the top, it's just the aluminum disc. It mainly has one electric dipole resonance. So without going too much into the detail, it means one broad resonance that covers quite a wide range of the spectrum. Here we're coming into the near infrared for that system. Here you see the silicon disc has a much more rich response. It also has some electric dipole resonances, but it has also some electric quadrupole resonances that appear, some magnetic dipole as well, which is the longest wavelength or the lowest energy resonance for this cylinder. And when we combine the two together, we have many different peaks, many interesting optical features. So what we tried to do with that was to make some sensing. We did bulk refractive index sensing. So the idea is you take your metasurface and you immerse it in different liquids, and you hope that the optical response is going to change with the refractive index of the liquid. So you see here in air, it's the red curve. These are all measurements. If we then immerse it in water, we see that the response changes. If we add some glucose in the water, it changes further. And if we add more glucose, it changes further, and so on and so forth. So to quantify this response, what we can do is to look at different features. We have many of these features. So like here, the little shoulder here, for example, and see how much its wavelength changes as we change the refractive index of the background. And by doing so, we obtain a value which is the sensitivity, which is just the change in resonance wavelength, so in nanometer, divided by the change in refractive index of the background. And the different features have different sensitivity, as we see here, but the most sensitive is number 2 and has a sensitivity of 200. So it means that if we change the refractive index of the background by 1, the shift of the wavelengths will be 200 nanometer. We were pleased to see this result, but at the same time, we were somewhat disappointed, because if you look at the state of the art for just simple dielectric resonator, you get a sensitivity which is better, 300 nanometer per refractive index unit. So it shifts more, it's more sensitive. And if you look at more sophisticated, but just plasmonic nanostructure, you can even get 600 nanometer. So this is not so good, but at least it's an interesting structure. And we try to improve it a little bit. And maybe I'd like also to make this point, which is, my feeling is very often when you work on an experiment, maybe you start by doing some calculation to have an idea of the type of structure you need to do. And then you make your experiment, you measure your structures, and very often you stop there. And I think there is a lot of value in closing this loop and going back to the calculation to try to understand what happened and even make it better. So in this case, we computed the field distribution for the structure we had fabricated with the silicone, the glass, and the aluminum. And we realized that all the light was actually trapped inside the structure. So it was not interacting a lot with the outside. So we thought, well, if we make our spacer a bit smaller, then the light will come outside of the structure and it will be able to probe the background better. So this can be done by making a wet etch HF step to do this undercut, and it can be fabricated. These are lovely little cupcakes. So we see the aluminum on top. Aluminum is very grainy. It doesn't really matter for this type of application, but it is quite grainy. We see the silicone in blue, and here we see in green the glass that has been etched, so has been recessed a little bit, such that the background can access the resonance better. And it helps. Doesn't help a lot, but it helps a little bit. We have an increase in the sensitivity of about 40 nanometer per refractive index unit. So this brings me to my summary. I've tried to show you that it's also interesting to question the way one fabricates nanostructures, and maybe there are other approaches than very standard one, which, for example, liftoff and maybe etching is superior for specific application. I think the bottom line is there is not one size fits all in nanotechnology. It's always important to try to think about different things, and often with the same equipment, you can fabricate with different approaches. If you can do that, then you can make some funny metasurfaces. Here we were interested in looking at this alloy. Also, I mean, when people speak about alloy, they will always speak about high temperature, but actually, especially for those two metals, it also works at low temperature. And finally, I think hybrid nanostructures are very interesting, very promising. Our first results are quite disappointing, but I think that's certainly a technology worth pursuing. All this is only possible because I have a very fantastic team. I'm sorry, the picture is a bit outdated, but they're still fantastic. We also have some difficulties with our website. If you need publication, you'll probably find them on ResearchGate, or you can just drop me a line. Thank you very much.
Thank you, Professor Martin, for this inspiring and interesting talk. Now it is time for a few questions. I see that there are already some questions on the panel. The first question is from Mariano Barella. Did you use any adhesion layer for the fabrication of the gold-silver arrays? If so, how optical properties change by introducing this material?
This is, of course, a very important point which has been studied quite a lot. There is a few works from Steve Blair from Utah who studied that. So indeed, often you use metal as adhesion layer, like chromium, and this can be detrimental to the optical properties. One must, however, keep in mind that it's very, very little. So you do a flash, and it's not going to make a continuous film. You deposit 2 nanometers, and it makes more islands of the material. And this indeed helps for the adhesion of gold on glass. For silver and for aluminum, if you look back, and I can send you also the papers, we did a lot of work on improving the fabrication of aluminum and silver. And there we found something very surprising, which is that silver oxide works extremely well as an adhesion layer. So silver oxide, you just start by evaporating a little tiny bit of silver, then you add oxygen in your evaporator. So tiny bit, it's again a few nanometers. You can find the description in the paper. We try to give as much detail so that it's easy to reproduce. And then on top of that, either you evaporate again silver, or you can evaporate aluminum. It turns out that both silver and aluminum have the same kind of crystal parameters, so they go very well together. As a side note, we have also, in developing this process, observed that we can stabilize silver. If you make sure that during the evaporation, you have almost no water in your system, you can keep your samples for months afterwards and they don't deteriorate. Also, we have a paper on that describes it. More recently, we've been trying to fabricate very high aspect ratio electrodes. So we had nanowires of gold that were maybe 200 nanometer wide and several micron long, and we realized that they were not stable at all. And using these metal like chromium, for example, adhesion didn't work. So more recently, what we have discovered is that self-assembled monolayer work very, very well as adhesion layer. And because they're very thin and dielectric, they do not disturb at all the resonance. I don't think we are the first one who have discovered that. I think there were a couple of papers that reproduce that. But if you think about it, if you have a monolayer and you would have thiol on one side, then it would attach very well to the gold. And you have another group like a silane on the other end that would attach to the substrate. And this works very well as an adhesion layer, yes.
Okay, thank you. Then there is another question from Marco Gandolfi. Could you kindly comment more on the applications of silver-gold alloys nanoparticles?
Well, I'm open for any idea. There is, and you are probably aware of that because you do biosensing, there is a huge literature about gold-silver alloy that are fabricated by chemical synthesis. I think the main applications lie in the fact that by adding a little bit of gold to silver, you can also stabilize chemically the silver. And that has been used, for example, for Raman. So silver has a stronger plasmon resonance than gold because the absorption is weaker. But again, there is this stability problem, especially if you want to go towards biology, because you will always immerse your sample into some liquid, and that could ruin your nanostructures. So having a little bit of gold can stabilize the silver, and you may still have strong hotspots in the silver, in the alloy, basically. So I think that's probably one type of application. For us, it was really just to play with the phase while maintaining the amplitude of the reflected light.
Thank you. Then there is a question from Mahmoud Ruzzi. The fabricated nanostructure surfaces seems quite rough. How would roughness affect the performance?
So this is, of course, a very interesting, important issue. Those here on the right of the screen, which are made out of aluminum, are indeed very rough because that's the way aluminum grows. The one here, gold on the left, are smoother. So it really depends on the material. Now to the question, the way we drive these structures is with light that comes from the top of the structure. And the electric field is going to be parallel to this little cap. So the fact that the top surface is rough doesn't really matter because the electrons are not going to be too much moving vertically. They mainly move in this horizontal plane. But still, overall, it's certainly not a very good thing to have structures very, very rough. If you want to have them smooth, I think there is a very nice field emerging, which has been initiated by Bert Hecht, which is to work on single crystal nanostructures. That works for gold. So it's possible to grow very nice single crystal nanostructure. And I think Julia can also tell you about how to make them very large. So that's one way. I mean, then you have to really try to use nature to make it such that things remain smooth.
Okay, thank you very much again. I think that we can move to next speaker. Thank you again. If there are other questions, you can take part in the final roundtable where all the speakers will be present and available for answers.
And I will also answer now in the chat.
Okay. Thank you. Thank you again, Professor Martin. And I leave the stage to my colleague, Dr. Attilio Zilli, who is presenting next speaker.
Thank you. Good morning, everyone. And so for those who joined